So hi everyone, my name is Colin Fulton. I'm a front-end developer at Duo Security, a division of Cisco. And this sitting right here in front of me is a vintage Apple IIc computer. Needless to say, this is older than me. And actually, just to give you a full demonstration of what's going on here, I'll turn the computer off. On this 5 1/4 floppy disk is custom written in assembly slide presentation software along with all my slides. The total code for this is smaller probably than the GIFs in everyone else's slides. So I'll go ahead and pop that in, turn it on. That knocking sound that you hear is because to save money, they didn't actually put a sensor in the Apple II to read where the disk head was. So when the computer first turns on, it doesn't know what sector it's reading. So it just bangs the head against the far side a couple of times just to make sure it's definitely in sector 1. Alrighty, so I'm gonna go ahead and run my slides. And it'll take it a second to load off disk. All right, so here we go. So first things, I need to actually make an apology because in the description of this talk, it said, come see Ruby running where it's never run before. Unfortunately, before I gave this talk, I found a couple of bugs and there were a number of implementation issues. Nothing that made it impossible and nothing that couldn't be fixed, but it meant that I wasn't able to get everything running so I could actually show you the code today unless you wanted to look at a bunch of assembly running, which is not very interesting. And so for that, I'm sorry, I'm not going to be able to give you a demo of Ruby itself running. However, I think you've all seen Ruby running before. However, I also said in the description that I was going to show you how such a rich language can be squeezed on such a really small computer. And that's what the majority of the talk was going to be about anyway. And so this you will see, how we actually managed to squeeze Ruby onto this little tiny thing. Alrighty. So first, before I can show you how we're going to put Ruby on there, I think it's important to know how programming used to be done, specifically in 1977, 1976, the way that Steve Wozniak originally wrote software for the Apple II. So I'm going to exit out of my slide software and go into what's known as the monitor. Now, when Steve Wozniak was originally developing the Apple II, he needed some way, he wanted to have a basic programming language on there, specifically the basic programming language. However, he didn't have the money to have all the debugging tools and assemblers that you normally had. And so he actually wrote out in machine code this particular program, the mini monitor, which lets you actually see what's going on in memory and disassemble code. And so he actually wrote all that out by hand in machine code, so then he could write assembly code in order to actually implement his version of the basic programming language. So I wanted to show you a little bit of what that's actually like. So in the mini monitor, we can look at memory. So at byte 800 in memory, it's a 0. If I say 800.8ff, that will show you all memory between 800 and 8ff. Go ahead and hit enter. There's a bunch of data there. And so we are going to write a program in machine code ye old-fashioned way. And so I'll say 800 colon, which says insert the following hexadecimal into memory. And what we're going to do is we're going to type in A0, 0E, B9, 0B, 08. I think you can all see where this is going. I'm going to do 99, 60, 04. I know this is really riveting. 88, D0, F7, 00. And there I have my program. However, I need a little bit of data to make this work, because I think you can all see this program isn't going to do anything interesting on its own. So I'm going to type in a little bit of data. Again, this is literally how Steve Wozniak implemented the program that we're seeing right now. All right, now I'm going to do 48, 49, 60. And this is where I think you're all going to get really excited is when you see this next part, because I'm going to do 52, 55, 42, 59, 60, And then this is the obvious bit, is where you do 4B, 41, 49, then 47, 49, and of course, to finish it off, because we want to be exciting, 61. We write that to memory, and there we have our program. Now, machine language doesn't look very readable, but it actually was a long time before we actually had the assembly programming languages in order to make it easier to write out machine code. There was a graduate student named Don Geils, whose job it was, as a graduate student, to take in the programs that professors and others would write and hand translated it into machine code. And he thought this was really time consuming, and so what he'd do in his free time was he started to write an assembler, something so that he could type in nice human readable commands, and then the computer would translate into this. And von Neumann, one of the professors of the university, von Neumann himself, the creator of the von Neumann architecture, one of the people who sort of developed the idea of computers as we know it today, he saw that Don Geils was doing this and stopped him, because he thought that was a frivolous waste of time. Why would you write a computer program that could write this for you? That's clerical work. That's not computer's job. You should just type all this out by hand. It's good for you. Now, I will say that this sounds silly now, but computers were very, very rare back then. You know, there maybe were only a handful of them in the world. And so what Don Geils was doing, or Geils was doing, was equivalent to one of us today using an entire supercomputer just to run our text editor. It kind of was overkill. All right, so I'm going to take my program, and hopefully, if I wrote everything right, if I write 800 and then G, it's going to execute our program. Now, I don't know if any of you have done live coding before, but I may have made a typo, and I have like a 50% accuracy rate on writing this program right. So if we run it, there, we see it flashes on the screen with hi RubyKaigi. Now that 0, 0 in the middle, there is a break command. That's what brought us back into the monitor. And we see here that M0, A, X equals, those are what all the registers had in them after it finished executing our program. If we disassemble the program, we can see a little bit more of what's going on. So I'll do 800L, and that's going to disassemble the program. And here we see the lines of our code. Then in the middle, we see the actual original machine code. Then we see the assembly. And I have this nice 1980s pointing device here, which if I switch on, will let me put an arrow on the screen. And I'll change the arrow direction. And so we'll look right here. First, what our program does is it loads the Y register, that's LDY, with a literal value, that's the hashtag, of the $, that means hexadecimal 0E. So we're putting the value E inside the Y register. Then we're going to go ahead and do LDA, that's load into A. Oops, this thing's a little bit touchy. We're going to load A with this next bit says whatever happens to be in the memory address 80B offset by whatever's in the Y register. So we're actually doing an indirect memory lookup. We're looking at another part of memory and loading that into the A register, offsetting it by what's in the Y register. We're then going to do STA, which says store whatever is in the A register. And again, we're going to use a different address in memory and then offset it by the Y register. We're going to decrement the Y register. We're then going to branch if not equal. So if that previous command, the decrement Y register, if it did not return a 0, so if we didn't decrement from 1 to 0, we're going to go ahead and loop back to 802, which is the second instruction in our program. And so it'll loop back until the Y register is counted down to 0, and then we'll hit the break instruction. And everything after that is just data. And what that data is the hi Ruby written out in flashing text. Now, flashing text is just a different part of the character set. The old Apple IIs didn't actually have lowercase letters, so to make up for that, they gave you, within their character encoding, all uppercase letters, then all uppercase letters with the character colors inverted, and then all uppercase letters that would flash different colors. So, you know, you don't get lowercase, but at least you get flashing text. So this is an assembly program that just writes that on the screen. Now, something to note here is that we're not like doing something special to the right to the screen. We're just writing to memory. The Apple II effectively just has a very large address space that anyone can write to. So that's your program, your data code, anything that's in there, everyone can just write to the memory. And inside that memory, there's one stretch of it that is whatever is being loaded onto the screen. And so if you, in your program, just directly access that memory and write to it, you can directly write characters on the screen like you did before. Now, programming assembly like this is really, really painful. It's not as bad as you might think, but it's still not the most pleasant thing, because let me tell you, I've been doing a lot of it recently. Using this mini monitor, Steve Wozniak implemented a version of the basic programming language to run on the Apple II. The version that he wrote, which later got dubbed integer basic because it didn't have floating point numbers, was really, really fast because he wanted people to be able to write games in it. However, it had a number of other limitations, so eventually Apple reached out to Microsoft. Microsoft provided them with Microsoft Basic, which got renamed to AppleSoft Basic, or FBasic because it had floating point numbers. And then that's what you generally see on most newer Apple IIs today. And so to go into BASIC, I'm going to do Command B and then hit Enter. Now, BASIC is a much, much nicer programming language to program in than assembly. And this is how a lot of people first learned to do computer programming. Many here today may have first learned by writing in BASIC. However, even though we're kind of used to the idea of BASIC being relatively simple, you can set some variables, you can do for loops, you can do gotos, you can do a basic if, and you don't have functions, it'll just run through your code in order until it encounters a goto. However, BASIC is not a great programming language. So let's have a variable here. We'll say our variable is going to be the word Ruby. And then we're going to say Ruby equals the string great, because Ruby is great. And it says type mismatch error, because it turns out you can't actually have variables like that that are going to be strings. They can only be integers. However, if we write Ruby and then a $, and then equals, and then again great, now it will actually store that as a string variable with the separate name with the $ at the end. This is okay. However, let's say that we have another string variable. We'll call it Rust $ equals, and we'll say also great. All right, because we're not going to be mean towards other programming languages. This is fine. And let's go ahead and print out what is in that Rust variable. And you'll see it says also great. Fine, this seems normal, isn't too bad. However, if we now say print Ruby $, it says also great. The reason for that is because AppleSoft Basic will let you have variable names of any length, but it only looks at the first two characters to actually distinguish between them. So since Ruby and Rust both start with the same two characters, you're kind of, you have to write some very interesting variable names to get around this. So I'm going to go back to my slides, call 1016. By the way, being able to switch programs like that, because everyone is sharing the same memory, is not the easiest thing in the world to do. This wasn't like you could run multiple applications on the Apple II, so I kind of had to fake it to make this work. But it is actually switching between BASIC and my slides. So, basic programming language. It's fine, but it's obviously not that good. It would be much, much better if we could run Ruby on the Apple II. And that has been my goal for a long time, entirely because last year at RubyKaigi, I had a conversation with someone. We started talking about old computers, and I mentioned this idea. Wouldn't it be nice to have Ruby run in the Apple II? Now, he had done assembly programming on the Apple II. He had been doing this a lot, and he said that that probably wouldn't be possible. I, however, had done no assembly programming and never written code for the Apple II, so I decided to see if I could actually do it. Not a great idea, but hey, I've had a fun couple months trying to make this work. Alrighty, here's an idea. Ruby's written in C, so if we just take C Ruby and compile it into the 6502 processor that's on the Apple II, everything will be great. We can actually run Ruby on the Apple II. Except there are a couple problems with that. One, C Ruby expects certain things to work, like a file system. The Apple II didn't have a file system. There were operating systems on top of it that had very primitive ones, but it's nothing like the file systems that that C Ruby expects, and so we'd have to patch over all that stuff. It also expects things like Unicode support, and the Apple II obviously doesn't have Unicode support. It also expects ASCII support, and though this Apple IIc can actually run in a mode that will have ASCII characters in it, when it's running in sort of the legacy mode like it is right now, it doesn't even have ASCII support. However, there's some even bigger problems. CRuby, the binary, the interpreter for CRuby, is over 3 megabytes in size. Now, you could get very late model Apple IIs that had like a megabyte of memory, and that was ridiculously large. However, the original Apple IIs, the lowest you could buy is with 8 kilobytes of memory. And remember that you're sharing that memory with the video display and, you know, all of the other code that's running. So obviously, it's going to be a little bit too big. And it's even worse than that because the 6502 processor, as we'll talk about later, can not do nearly as much as modern processors. And so it would have to add a whole bunch of extra operations, and your code would be much, much larger, almost certainly, than those 3 megabytes. All right, so there's mRuby, embedded Ruby. That's made to be a really small Ruby that can run on small devices like this. So obviously, we'll just compile mRuby, we'll put it on the Apple II. Everything will be dandy. Still too big. mRuby is a lot smaller, and there are a lot of really good talks going on right now about making it smaller and getting it so you can fit in smaller spaces. However, usually what they're focusing on is getting it so you can have very small amounts of RAM, but then store it in rather large amounts of ROM. And in the Apple II, the ROM, you can't write to. That's all the internal stuff for running the Apple II itself. And the RAM, we're going to have to put Ruby in RAM, and so we need to be really, really small. The other thing is that mRuby, though this is again being worked on right now, it's not very, very well optimized for 8-bit CPUs. Ruby expects, large pointers and things to be able to move stuff around. And while you can do that, this is an 8-bit CPU. It only operates on numbers between 0 and 256 at any given time. And so mRuby really just doesn't work out because of that. Again, this is being worked on. However, it isn't quite there yet. The other thing is that the C programming language is kind of too high level to do what we need. Now, as Ruby programmers, you're all laughing at the idea of C being a high-level programming language, but C is, by definition, a high-level programming language. The traditional definition is a low-level programming language is one where you can directly look at the code and translate it directly into assembly without any ambiguity. A high-level programming language is one where you can have the code and it will always do the same thing, but the assembly that it gets translated into could be anything. And this is how, optimizing compilers work with things like the C programming language. And so because we don't have direct control over all that machine code that we were looking at before, it means that we're not going to be able to optimize things and squeeze stuff down as much as we might want to. And thus C is too high level, and mRuby and CRuby are both written in C, so that's not very good. So is all hope lost? Are we not going to be able to run Ruby on the Apple II? No, we're going to do it the hard way. We're going to create nRuby. What is nRuby? It's all the joy of Ruby, it's just really small. Really, really small. We're gonna have to give up some features, but you know what, that's okay. I feel great being up here at RubyKaigi where people are talking about all these performance optimizations and awesome stuff going on in Ruby, and I'm talking about running Ruby on computers that no one uses anymore, as well as we're gonna make it way slower than most other Rubies. But nRuby, again, is really, really small. It's entirely written in assembly. I should mention that before working on this, I had never written any assembly because I don't have a computer science degree. I have a degree in art and design and theater. So step one was learning assembly programming, which is not as bad as you might think, but it was an interesting adventure. Now, what does that N in nRuby stand for? Does it mean nanoRuby? You can think of it that way. But actually, the reason why I called it nRuby is because an N is just half of an M. So mRuby is too big, so let's just chop off half that M. We'll call it nRuby. Alrighty, so let's talk about the design of nRuby. How are we gonna, make something that we can still call a Ruby, but be relatively small? What are our design constraints? So one, we need that nice flexible Ruby syntax, the ability to call methods both with parens and without parens, and all the other nice things that you can do within Ruby, and have everything be an expression so we can nest things in all sorts of fun ways. Cool. We also want it to be pure object-oriented, so even integers are going to be objects in nRuby, and they are. And this does mean that our code will run slower, but hey, if you wanted fast code on the Apple II, you pretty much have to write an assembly or, a faster language like BASIC. All right, And we also need to make sure to include all the features that people love. So we need, in addition to classes, we want modules, the ability to compose code together. This isn't actually that complicated because all that a module is just kind of this bucket or an array or a hash of different methods that we can include elsewhere. And so it's not that hard to implement modules. Blocks are a little bit more difficult, but at the end of the day, the actual content of a block is a static bit of code, so we can just store that the exact same way we store the code for any method, and then just store metadata about all of the local variables whenever we have to generate an instance of that block. We need IRB, or I guess I should call it NIRB, NIRB, which is kind of a terrible name, but whatever. We need an interactive way to program with it, which isn't too bad. We want things like enumerables. We don't want to have to deal with for loops because, we're not C programmers, we're Ruby programmers. We want each and map and reduce and all those fun things. And we want eval. Or rather, I want eval, because I want to be able to write quines in this, because it's not the Ruby programming language unless you can write a quine in it. So I'm going to make sure to include eval. You also kind of need eval for IRB to work. All right, we need the language to be more dynamic than anyone needs. So you need to be able to, redefine methods as you go, which actually is relatively easy. Instead of, having two separate ways to define method, one for statically defined methods and one for dynamic ones, we just have our stuff that statically defines method call the dynamic method generation code. It'll be slower, but who cares, we're running on an Apple II. And you need to be able to redefine all methods, which means you can redefine the plus operator on integers. Now, the only reason why this is bad is because it makes things slower. However, if you've never redefined the plus operator on integers, I'd recommend doing it because you can write some hilariously bad Ruby code by doing that. All right, we need dynamic memory allocation and GC. This is where things get a little bit more tricky. We don't have that much memory to work with. My main goal is to get it to work so you could theoretically run it on 16 kilobytes of RAM. That includes all your program data, your program, as well as the entire nRuby runtime. And so we need to get really, really small garbage collector and some really clean memory allocation code. You need to be able to make as many objects as you want. Just, create objects all over the place and not really worry about it. However, I did put this other design restriction in. You can make as many objects as you want, as long as you want 256 objects or fewer. How many of you here have ever written a Ruby program that uses more than 256 objects? All right, if you're not raising your hand, you're lying, because when you boot up Ruby, it creates far more than that. But I think 256 objects is enough. We can write nice, small, compact code, and we can run stuff. The reason why it's 256 is it means that we can uniquely identify every single object in memory with 1 byte. That means our object identifiers and our pointers in memory can be 1 byte long, which makes things a lot more compact and means that we can squeeze in our allocation in GC into the very small space. All right, so assembly. Scary programming language. I think it was either the #1 or #2 most hated programming language on the most recent Stack Overflow survey, which is weird because I'm pretty sure most people responding have probably never written that much assembly, but still, everyone seems to hate it. However, it's not that scary. It's less scary than you may think, so let's look at what you can do with assembly. One, you can do things with a register. So you can increment a register and just say, add 1 to it. Registers, you can think of them as just like variables that your processor has. You have a limited number of variables you can operate on. And so you can increment a register. You can add a register with another register. Not actually on the Apple II, but we can talk about that later. You can, do bit shift operations, things like that. You can manipulate a byte in memory. So you can say, store this register at this byte in memory. Or you can say, hey, take this byte in memory, increment it by 1, load it. There's not that much you can do with memory, but you don't need to do that much. You can jump to another part of the code. So you can just say, I'm currently at this part of code. Can you jump to this other address? Or you can do conditional branching. You can say, if this particular register has this particular value, jump over here. If not, just carry on. And then the syntax is actually relatively simple. It kind of looks scary at first, but it's one of the simplest syntaxes you can really ever have for a programming language. So in the far left column, there's optionally you can put in a label. all that the label is a variable that your assembler defines to say whatever command follows next, take the address of that command in memory and store it in that variable. So that lets us say jump to this particular command because that label is storing that address in memory where that particular operation is. You then have the mnemonic, which is a terrible term, but it's the term that gets used. The mnemonic is the little three-letter code that you see that tells you what command you're going to run. That's the only required bit. So the mnemonic it's a shorthand for one of those little machine hex codes that we were typing in before to run a command. And then some of those mnemonics require an argument. And that argument may be a literal value like you saw before to insert something into a register, or it may be an address that you need to pull something from. LDA, that's the mnemonic for the load A register like we saw before. Again, the hash just means load a literal value. The $ means the value is going to be hexadecimal, and 00. So what this command will do is it'll load 0 into the A register. CLC means clear the carry flag. So whenever we do add operations, a flag will be set to say whether or not we overflowed or carried in some other way. So we need to clear that before we do any addition. So next we have a label loop, so that all that label there says is just store whatever the address in memory of the next line is in a variable called a loop. And that is only stored in the assembler. It later gets translated into an actual number. ADC, that says add the following number to the A register. And then we're going to add the number 1. Then we'll go ahead and do compare with count. Count is just a variable which again points to somewhere else in memory. So compare the A register with whatever's in another address in memory. And then BNE, branch if not equal. If that compare operation showed that the A register wasn't equal at that address in memory, you're going to jump to where that loop is, and it'll go ahead and jump there. And at the end, BRK, that just means break or end the program. It actually sets the interrupt register and does a couple other things, but we don't have time to get into that. So what does this program do? It loads the A register with 0. It then adds 1 to it. It compares it to some count we stored in memory. And until A is up to the number 1, it is going to just keep looping through this code over and over again, adding 1 to it until eventually A equals whatever the count is. There also are things like increment and decrement operators, which are easier ways to add and subtract 1. However, on the 6502, the processor in here, you couldn't actually do increment or decrement on the A register. Alrighty, so a quick intro to the 6502. I keep mentioning this thing. This is the processor that's in the Apple II. It's also in things like the Nintendo Entertainment System, the Commodore 64. It was a really, really popular processor for the time, largely because it was cheap and it was relatively nice to program for. However, the reason why it was cheap is because it was very restricted in what it could do. It was an 8-bit processor, as I mentioned before, so you can only operate on 8-bit numbers, which again is 0 to 256. You have an A register, that's your accumulator. You can do most of the operations you can do on the A register, so this is where you're going to store most of your results and do most of your math. You then have an X and Y register. These are additional registers that are provided for indexing into different parts of memory. You can't do addition or subtraction with them. However, you can do certain other operations with them that you can't do at the A register. It's hard to say how many registers or general purpose registers are in the 6502 because the A register can do most things, but it can't do everything. But it's the most like general purpose register that we have. And then X and Y, there are registers that you can do some things with, but you can't do as much as the A registers. That's why I don't say how many general purpose registers there are, compared with like an x86 processor, the modern processor in your computer, which has a lot of registers in comparison, and you can do all operations with those general purpose registers. There's a flag register. That's where it stores various flags. For example, did the last operation return a 0? Has an interrupt been registered? Was there an overflow or a carry that needs to be run? There's a stack pointer register, so that's a point to a stack. There's actually a hardware stack inside of here. Now mind you, that stack is 256 bytes long. It occupies 1 page in memory. So you can't have a really deep call stack with this. However, you can do some stuff with it. And you can also directly push and pop values onto it. There's a program counter. You can't really directly access that, but that's where the 6502 stores where you currently are in the program. Whenever it runs an instruction, it will generally increment that by 1, so it runs the next command. Or if you run a jump instruction, it will replace that with whatever you give it. Instructions are 1 to 3 bytes long. This is very, very small in comparison to, for example, the x86 processors that most computers run today. Their instructions are, I don't know, anywhere between like 12 and 86,000 bytes long. There are some really, really crazy operations in x86. There are 56 mnemonics for instructions. That may seem like a lot, but compared to a lot of computers today, that's not very many. Because each actual machine code instruction only takes up 1 byte, that means that they only had between 0 and 256 bytes they could occupy, and they didn't even use all of those. So we have 56 kind of operations that we can do on this computer. There's a 16-bit address space. That means that we can address 64K of memory or controllers or various things on there. However, you may notice that we have 8-bit registers, but we can do 16-bit addresses. How on earth does that work? Well, you can point to either literal addresses, so if you know the address ahead of time when you're programming, you can just hard code that 16-bit address, or you can do fancy stuff with a thing I'll talk about in a moment called the 0 page, where you store an address in memory, operate on memory, and then say, work on whatever address is stored here in memory. And so you have to do all this crazy indirect stuff entirely because you can't hold an entire pointer inside of one register. Alrighty, pages are 256 bytes long. So pages are, sections of memory that you can operate on, and some operations are restricted to a single page. And there are 2 pages in the 6502 that are special. You have the page 1, which is your stack, and then page 0, which is a special page where you can go ahead and do very quick operations. And I spent way more time on this than I probably should have. So let's jump into how you do garbage collection. So how are we going to do garbage collection on this tiny computer? C-Ruby uses what's called a mark and sweep garbage collection algorithm. You could do an entire talk on this. Suffice it to say, it's really good. It has a lot of benefits. However, it's very, very complicated, especially C-Ruby's mark and sweep garbage collector has all sorts of performance optimizations and nice things going on. We're not going to be able to do mark and sweep garbage collection, but we can do reference counting. Anytime we add a reference to an object, so anytime we take an object and add it into an array, we just increment a number by 1 and say, okay, that's going to be the reference count for this object. If we ever pop an object off an array, we're going to decrement the reference count by 1. So we'll just keep track of how many references there are. And if that count ever hits 0, we know for a fact that there are no references to the object, and we can go ahead and just clear it out from memory and let that space open up for someone else to use. However, there are some serious disadvantages to this. It means if you ever have a reference loop, you'll never garbage collect that. There are ways around that. However, we don't have time to get into that. Alrighty. So the way in NRuby that we store stuff is we have slots. Each slot is 16 byte, and that'll store the smallest unit of an object. So an object is at least 16 bytes large. We have page 0, page 1, and page 2. Going all the way to page 16, and then we have 16 slots in every single thing. So whenever we want to allocate new memory, all that we're going to do is iterate over each one of those slots, wait until we find one that doesn't have any data in it, and then just put stuff in there. Then whenever one of those slots is freed, which means the reference count hits 0, we know that we're safe to overwrite it. We'll just keep looping through until we find space. If we loop through all of them, we can't find space, we just have to throw an error, because congratulations, you have more than 256 objects. We don't have any more room to code it. This means we have a total of 4 kilobytes of space to store objects in, but that's actually a lot when you consider how limited this computer is. Here's how we actually lay out objects in memory. We have our reference count, which is just going to be a number between 0 to 56. We have an ID, which that's a pointer to whatever object has the class of this object. We have the size of the objects. That way we know how to iterate through it. Then we can just store a bunch of data. And if the object is too big to fit in here, in the very last slot, we put an ID into the next slot. And so we can then have another slot in memory that'll store additional data. And so now we have a linked list storing all the data for our object. Cool. So how do we go from that single byte to calculate the object ID? All right, so let's say we have an object ID of CF. That's going to go to byte 240 or F0 or page 12, 0C in memory. And so we need assembly to do that. We don't have time to go over all this assembly, but effectively you'll note that C0, which is our ID for the object in memory, the C gives us the page in memory, and the F gives us the byte in memory. And so our nibbles actually give us the page as well as what byte. So what we do is we just shift that F over to the left. That's the ASL operation, arithmetic shift right. We shift all those bytes over. Then we have LSR. We shift all the bytes over on the other side. We get our two addresses and we store them. This is fine. However, because we are writing to memory this way, where all our slots go sequentially on each page, it's actually more code than we need. If we instead flip our memory addresses, so instead of it going page 0, 1, 2, 3, 4, we say on page 0 we have slot 0, page 1 we have slot 1, etc. Instead we flip it so it rotates 9 degrees, goes the other way. We can write much smaller assembly by instead just kind of doing some bit twiddling. And if you're not quite understanding what's going wrong on here, don't worry. I don't really remember how all this works anymore either. We'll get into that later. However, what we do is we can instead still use the C and the F to tell us the page. We just flip which one talks about which. And if you want to know more about this, we can talk about it later. And so here we'll see our code before and our code after. It's shorter, it runs in less time, it's a lot better and more efficient. Alrighty, parsing Ruby syntax is going to be really hard, right? This is going to be really difficult? No, not really. That wasn't really that challenging as it turns out. So first we need a way to parse symbols. For example, you can think of these as tokens in a normal parse, or atoms if you're used to Lisp. It's a unique integer to identify any sort of string that we have. So for example, def, if, a variable name. What we do is we put a table in memory where we do a bunch of space-separated words. And then what we do is we take our bit of code and we look at that def there. It starts with the letter D. The first thing in the symbol table, does it start with the letter D? No. Move on to the next one. Start with the letter D? Yes, awesome. Move on to the next letter. E, O, those don't match, so we have to move on to the next one. D, that matches. E, that matches. F, that matches. We're at the end. Cool. Def is the third symbol in the table, so we'll give it a unique ID of 3. We've just taken our string, which was 3 bytes long, and turned it into a unique ID that is only 1 byte long. So we can go through and do this for all our various code. And now we can take and sort of tokenize our code into a much smaller format. So let's look at an assignment statement. X equals 10. So what we'll do is we'll look at that X, we'll find the ID for that particular symbol. We'll then look at the equal sign. We'll say, aha, that means we have to do an assignment. Let's remember that. Then we see, okay, what's the expression that we're going to be assigning with the value? It's a 10. Okay. We're going to put out a opcode to say store a literal int on the stack, and then those are the 2 bytes for 10 on the stack. And then because we're doing an assignment, we're going to pop that value off the stack using op set local. We then have the symbol name, x, so we want to set the local named x, which in this case would be 4c in the symbol table. And then we're done. Ruby has ambiguous syntax, so if we have the word smorp there, is that a local variable? Is it a method call? I don't know. So what we're going to do is we're going to find the ID for that symbol, and we'll have a special opcode that just says, look, first try looking up a local. If you can't find one, try calling it as a method. If you can't do that, error, it's not found. And then we just need to store the symbol for that. So now we have that nice ambiguous syntax where you can do method calls and variables kind of in the same way, which makes your code nice and small. All right, so then we have something like this, a dot call. This may seem like this is going to be more complicated. It actually isn't. So first we put out an opcode to say call or put out a local. Again, the symbol is going to be DE. That's our foo. That's the ID for that symbol. Then we're going to go ahead and do a dot call operation. That just says pop whatever's off the top of the stack and call a method on it. The method name is going to be this 6a, which is the ID for bar. Then we're going to go ahead and say that we need to pull up the baz there. So again, opcall local baz. We're then going to take that result, push it on to an array that we stored on the stack to collect together all the arguments for bar. Say that we're done with collecting our arguments. You can go ahead and run whatever that dot call bar should run, and then we're go ahead and done. String interpolation, you'll see there I used square brackets instead of curly brackets. The Apple II didn't have curly brackets. This is what we have to do. This may seem like, oh man, this is going to be complicated. It really isn't. We first just push a string literal onto the stack that stores the first part of the string. We then close the string, so we do it as if we did hi close brackets. And then we just insert a plus operation. So create a string that says hi, and then add onto it the result of calling that name thing, and then go ahead and do that. And then we're going to go ahead and call another plus operation to add in the exclamation point at the end of the string. So even string interpolation, it's not actually that complicated. Integers. Integers are actually really complicated. This is a bunch of ASCII text. And so how are we actually going to make this work? You can ask me about this later, but here's how we do it. First, we need to set the running total to 0. Then we need to go ahead and multiply that by 10. How do we multiply by 10? Well, it's very simple. We need to copy the running total. We need to do a shift left. We need to do another shift left of the running total. We then need to add the copy that we had back into the running total. Then we need to go ahead and shift the running total left again. This gives us x plus 2 plus, or x times 2 plus x times 2. I don't know why those came out as minuses there, which is equivalent to multiplying x by 10. Awesome, we've now multiplied a running total by 10. Then we need to convert that particular first character there, which is a 1, into an integer. And that's very simple. We just subtract b0 because that'll shift it over to the right amount. Then we need to go ahead and add that into the running total. Then we need to loop multiple times in order to go through all the various digits, and then just repeat that until finally we have the integers. This was really hard and really annoying to write, but it works. And we have to do overflow checks every single step of the way because someone could be a jerk and write a number that's larger than 16 bits long. Alrighty, so then once we do all that, we can put out a literal integer opcode and then put in the values that we generated. Awesome. I did not think that integers would be the hard part of Ruby syntax, but apparently they are. All right, so how do we actually get this code running? How did I do all this development work? I did test-driven development in assembly. So I wrote a very, very small testing framework that would check the result in the A register against some value that I set ahead of time, and then it would print characters of the screen to show that they pass or fails. I don't know how anyone does assembly without test-driven development. It makes your life so much easier and refactoring so much better. You could develop on vintage hardware. I would not recommend doing it. It's kind of slow, kind of annoying to do. However, there's the Virtual 2 emulator, which is what I use, which is a great Apple II emulator. It lets you directly inspect what's in memory and kind of muck around with things as your program runs. There are other emulators out there that are really good, so it's just a matter of taste. I use the Merlin 32 assembler, which is actually a direct descendant on an assembler originally written for the Apple II. CC65 is another option. That will actually has both an assembler and will let you compile C code to run on the Apple II. But as we mentioned before, the C code it compiled is way bigger than anything that you'd ever write in assembly code. Apple Commander is a Java program. I don't know why it's written in Java, but what it'll do is it'll take a binary for the 6502 and turn into an Apple disk image. Awesome, now we have an Apple disk image that we can run on our assembler, or run in our emulator and load it in. And then we can use a program called ADD Pro, which lets me hook up this crazy cable, which now I own and need to figure out other things to do with, plug in my modern Apple computer to this Apple, vintage Apple, transfer the data onto it, and save it onto disk so I can actually get real floppy disks running my program. Alrighty, so what's next? I need to finish version 0.1 of NRuby. Please follow me on Twitter if you want to see when this actually starts running. And I want to see if I can get NRuby running on other processors. For example, there's the MSP430, a modern processor which I really like. It's really small and really, really low power. So theoretically, if we can get NRuby on there, it means that we can have Ruby actually running based off the power generated by a lemon. Like we plug in 2 pieces of metal into a lemon and use that tiny voltage to power a chip running Ruby. However, it's even smaller and even harder to get stuff onto there, so we'll see if we're going to be able to do that. There also are other computers that run the 6502 that I'd love to run with. The NES, the original game system, it only has 2 kilobytes of RAM and 40 kilobytes of ROM on the original cartridges, but hey, could we run actual Ruby programs on an NES and write games, very simple games? in Ruby. I think that would be really cool. If you have any questions, feel free to see me afterwards. I'll also be on the top floor during the break, and you can go ahead and come up to me. We can play with the computer. I can also show you more of the assembly code if you want to go more into that. Again, at Peter Quines on Twitter, follow me if you want to actually see the final result of all this once it's up and running. GitHub at Just Colin is where it be. I also will be posting my slides, so if you ever want to give a presentation using an Apple II, you can use my source code. It'll be open source. Because why not? And you can email me at justcolin@gmail.com. And thank you very much. Arigatou gozaimasu.